Sup guys, welcome to today's show. Today we are going to start a new project and I will code something called FSE. And I'm gonna wait a little bit by telling you all what that stands for, because that would ruin the surprise for next week's project. But we are going to focus on the ending E in FSE today, and this is a file encryptor. So we have two different files. We have FSE, which will encrypt a file. You just give it a from and a to. And then we have FSD, which will do the reverse. It will decrypt the file. It will ask the user for the key, and here is the thing which makes this project interesting. At least I think so. The program will be able to say wrong key. If you type the wrong key, the program will be able to detect that, and if you type in the right key, the file will be decrypted accordingly. So why is this interesting? That's kinda self-explanatory, isn't it not? Well, it's not very easy to do, because if we're using the encryption that we did a couple of lectures ago, when we wrote a project called R4. If you missed that episode, that was an episode about an encryption library, which uses the RC4 stream cipher, and it doesn't matter if you haven't seen that episode yet. You will still be able to code today, but you will need to link that the library when you compile. So let's say we have a program that looks pretty much like this. We give two arguments, two files, and we supply a key which is not being echoed to the terminal, and we just use the ARC4 to decrypt the file. Then it will not fail if the key is incorrect. The only thing is it will produce the wrong output. So the output file will be a lot of random garbage, basically. And if you provide the correct key, it will be the right file. And that makes it very difficult for checking if the key is correct, because the program does not know what kind of a file this should be. It could be a regular ASCII text file, like in this case, but it could also be any type of binary data, like a MySQL database file or anything really. So it's impossible for the program to use the output file to see if it has worked. You could do some form of analysis and have some kind of fingerprint database for different file types, I think there is something with relate to MIME you could use, or there is also a Linux command which is, I think it's just you type file and the name of the file. I think that is it. But that is not 100%. It doesn't know every format out there. And even if it correctly identifies the format, there is nothing that says it can't be two different files with two different keys with different contents of the file but the same format. So that is doomed to fail. The only way to be able to do this will be to include the key somehow in the input file. Okay? But there are a lot of pitfalls when you try to do something like this. Because if you make one wrong move, you will either make the encryption very easy to crack, or it will be worthless. Okay, so how can we go about this? Well, one way would be to, let's say this is the file contents, the clear text file contents, and let's the thing on the right be the ciphertext. So CLCI. And this is not even relevant for us right now, because the decryption tool will only be dealing with the ciphertext file. So let's focus on this one instead. So what can we do? Well, we can take the encryption key and put it in the beginning of this file in the clear text. So let's say if the key is tomatoes, then we put the regular ASCII string tomatoes at the beginning of the file. And then we either have some kind of separator. Let's say we have a double pipe sign, and then the actual file contents start. That's one way. But we are talking about the ciphertext. This is an encrypted file. So if we have the key in clear text inside of there, it would be a problem, obviously. We could, however, still keep the key right there, but we encrypt it. So basically we just add the key in clear text to the source file at the beginning, and then we encrypt this, and then we continue on encrypting the rest. And of course this is more secure than the first option, and this might be kind of tricky to crack, but we will most definitely open it up for making the security less than if we didn't have the key right there. And we don't want it. The task is to make this possible, but without in any way making the encryption less safe and easier to crack. So, and why is this decreasing the security? Well, when you try to crack something in encryption, you want to have small pieces of information. Well, actually, you want a big part of information if you can get it, but basically cracking depends on you looking for weaknesses, looking for patterns in the algorithm, in the output, in the way the key is generated, in the way you do random bytes, etc., etc. And if the coder does something wrong, it gives the cracker information, and every zero or every one of information that they obtain will make it easier to crack. It will lower the possibilities, because a cracker usually it makes a computer test every possibility according to some scheme. And if you have parts of information, then you don't need to crack every combination. You can leave something out. And this can also lead to more information because of other small bugs, etc., etc. So if the cracker knows that the beginning of the file, and we know how big the encryption key is, it's somewhere between 1 to at most 2048 bits. So in the first 2048 bits, we know that the key will be stored, encrypted in the same way as the rest of the file. And this is a lot of information, and it's a very, very important information. So this will most definitely lower the lower the security of the encryption suite. Okay, so this is not a valid way to do things. Let me just clean this up a little bit. Okay, so what else can we do? Well, we can take this. Usually you don't store passwords in clear text, not even in an encrypted file. What do you do with them? Yes, you create a hash. A hash is a one-way encryption between quotes, because it's not really encryption. It's hashing, but you can describe it in one sense as a one-way encryption. So if we take our key, for example, we can turn it into a string of bits. And no matter if you obtain this string of bits, you cannot go in the opposite direction and reobtain the key. The only thing you can do is, if you try out a password, for example, then you can encrypt it the same way, and then you can look at both results and see if it's the same hash. That's the only way that you can use a hash. So let's do that. Let's select a hashing protocol. it will probably be some of the SHA hashing algorithms. There is SHA1, and there's I think 128 is one of the more secure. I need to check up on that. But one of these SHA ciphers, and I don't know exactly, but this probably means that it's 128. But anyway, let's say the first 128 bits of the file will be that encrypted hash. Well, that makes it better because the SHA hashing algorithm is most definitely stronger than what we had before with just Arc4. Okay, but this is still not good because of the same reason as the last time. If we do this, then the crackers will have absolute knowledge of the first 128 bits of the encrypted file, even though it's hashed, and they won't be able to use that per se in order to turn it into an encryption key, but they may still use informational parts of it in order to crack the cipher in other ways. So we don't want to do this, but we still want to use the hashing algorithm, SHA. But where do we store the hash? What if we put it on line 5 or something, a couple of characters in? Well, we still would have the same problem because it's an open implementation. The crackers will still know where this will be found. So we need to store it somewhere in this file, but different places every time. How can we do that? And how can we find it the next time? My idea is when we encrypt a file, the first thing we do is we produce a random value. Let's take a new page. So first we do a random value of 16 bits. That will mean a number from 0 to 65,535. And I will not use the 0, so this will be 1 to 65,536, I think. I haven't decided that, by the way. Let's do 0 for now. Okay, and where are we going to put that number? Well, first of all, we're going to put that random number, let's call that the offset number. Yes, this is the offset. So the first 16 bits will be an offset. But now you might go, wait a minute, isn't this the exact same problem like we had before? That the crackers will know exactly what this part of the file will be. Well, will they now? First of all, this is a cryptographically secure random value, which means it can be anything between 0 and 65,535, which makes it 100% impossible to do anything with, because you cannot turn it into something else, you cannot reverse engineer it in any way. So this should be secure. And what do we need this number for? Well, let's say we randomized the number 650. The next step will be to produce 650 encrypted random bytes. So the same cryptographically secure way that we created this random value, we will create a padding. And that will be somewhere from 1 to 65,535 bytes this time. Of random data. Which means that this offset will be exactly as secure as this offset thingy. Let me color this in. So the offset will be this yellow part, and then we will have our padding. Like so. That's the padding. Okay, and what comes next? You guessed it. The hash. And let's color the hash green. This is a little bit smaller. Maybe like so. And the rest, let's make that this color. This will be the actual data. And in this example, this looks like the data part is very small in comparison with the other, and it might be if it's a very small file, but more probable is that the next like couple of pages will be the data. So the data can be like several gigabytes. It can be any length, and then we will encrypt everything. So let's do something like this. So even the random data will be encrypted as well, and then written to the file. When we go the other direction, when we want to decrypt this file, well, then the program will ask us for the key. When we input the key, we will initialize our encryption engine with that key, and we will begin by decrypting the first 2 bytes of the file. containing the offset. And now there's two possibilities. Either we have the correct key and we get the correct offset value, or we have the wrong key and we get any random number between 0 and 65,535. Oh, and let's say we did get it wrong, the wrong encryption key, and this number is, let's say, 30,000 or something. What we'll do is we will skip the next 30,000 bytes, but as we pass through it, we will decrypt this data as well. And that is so the internal state of the encryption engine will be correct when we will start decrypting the real data. And then we are at place 30,000, where we believe that the hash is located. We can't really see if there's really a hash there, because the hash won't be in any ASCII format. It will be in a binary format, taking up like 128 bits in this case. So we will read that data. We will read the wrong hash and compare that to our wrong password, which will not work. And then we can say wrong key. For it, in order to, and then the program terminates. For it to really work, we will have to do this again with a real password, the real key. So let's say we have the real key this time. We will decrypt the first 2 bytes and we will get the correct offset of 650. We will jump past these 650 bytes, but we will decrypt them one by one as we pass them by. Then we will take the next 128 bits, which we think is the hash, but maybe not. Then we will encrypt our key with, we will hash our key, and we will get a hash back. And this hash we will compare to this hash. And this time we will succeed. So we can tell the user correct key decrypting. And then we will decrypt the rest of the file 1 byte at a time, all the way through, and we will write only this blue part to the file, discarding the offset, the padding, the hash, and only writing this blue, which will be clear text data. So this is my idea, and I think it's gonna work, that it's gonna be a secure way of using the ARC4 cipher. One prerequisite is that we use the whitewashed feature from the library that I showed you last week. But those two in combinations, this way of handling the files and the hashes and the keys, etc., in combination with a secure way of creating keys, that would be the third. But most important, we will have this way of expressing if we have the right key or not, and we will have the whitewashing feature to don't be affected by most of the recent bugs, etc., which has been found in the ARC4 cipher. So I believe that this is the solution to creating this ability to say wrong key if it's a wrong key without in any way decreasing the security of the encryption engine.